Okay, now we reach the part of the actual, I don't know, advice or something. So, okay, that was not half an hour. Okay, I'm trying to go fast, sorry. Lack of rehearsal. So, these are some recipes or tricks or tips that I have. Don't trust me. Like, go talk to someone who really knows this. But this is more or less what I have used and think. So the first thing is read the manual. Not the whole manual, it's like 1,000 pages, but like when you want to do something, go and read the section of the manual that you want. You can learn a lot. And there's a chapter 10, tips and tricks, but I would say some of the tips are kind of outdated. So this is, I'm talking about Orca because this is the only program I use. Then you can read tutorial reviews. You don't need to read everything, but you can look at the tables and graphs and try to see. So this is okay. This is like a graph of different functionals for different purposes. So the green is good, the blue is recommended, and the yellow and red are like not so good or bad. So basically it tells you if you want to, like PV0 is good for structures and frequencies. This is double zeta, basis set, triple zeta, and quadruple zeta. It tells you quadruple zeta basis functions with PV0 for this is excessive. You don't need that. You're not going to get anything better, and it's going to cost much more. Then, okay, we'll tell you different shortcomings of different methods. So this hybrid with double zeta basis sets will not work very well for reaction energies, will have errors. So the green things are good, and the blue are the recommended ones, depending on, okay, the criterion of the authors, which are there. So there's Stefan Grimme there. So basically, these are some of the range-separated hybrids, omega B97XV and XD4. The V is the van der Waals dispersion method. D4 is like this dispersion empirical dispersion. So this would be recommended with a quadruple zeta basis set for reaction energies and barrier heights. So that's, recommended by them. But you can also use maybe the green things. Okay, sorry. Okay, you cannot. Maybe this one. You can use hybrid with a quadruple zeta. And then these are composite methods that they developed, which have different corrections, dispersion and self-interaction error and other stuff. These are methods, B97-3C, R2-SCAN-3C, PBH-3C, are much cheaper usually than similar quality methods, but they are quite good for a lot of stuff. So they are recommended for geometries and stuff like that. And I used B97-3C a lot for geometry optimizations. Actually, even for calculating redox potential, it gave me better results than using a hybrid functional like PV0. It's actually quite good. And it's much faster than PV0 optimization. Okay, there are many other options. This is another like a big benchmark paper, and it gives you like for each kind of, has all these functionals, but for these are like a GGA, these are I think a hybrid GGA, or no, these are, I don't know, these are GGA, these are meta GGA maybe, and these are hybrid ones, including meta GGA hybrids, and these are double hybrids or stuff like that. And the red ones are the best ones of each category. So like the best one should be for the overall data set should be DSD BLIP, but then the best one of these are double hybrids, but the best one that's not a double hybrid is omega B97XV. So that you can go for that functional if you want good results and stuff like that. You can see here maybe B3LIP is somewhere there, I don't know. Okay, somewhere, I don't know. But you can use that to have an idea. Then, if you want to do calculations, you have to think first, what do you really want? Do you want the structures? Do you want different oxidation states? Do you want to calculate reactions or you want to calculate like constant for dissociation of protons or another stuff? Do you want to calculate spectra? Do you want to whatever? Like what you are going to do depends on what you want to calculate. You don't have the same recommendations for everything. So what I do usually is a geometry optimization and frequencies using a chip method. For example, what I call chip, it depends. It could be B973C or it could be PB0, but with a double zeta basis set on everything and triple zeta basis set on a metal. So I calculate a chip energy, and chip gives free energy through the frequencies, and then I do single point calculations on the optimized geometry with a more expensive method, which could be PB0 with DFT I ZBP. And then I calculate the corrected gives free energy from this formula. Basically, I take the difference between G and E and add it to the E of expensive. And then, okay, I calculate properties, sometimes with the same function, sometimes with other more specific options, depending on what you want. So these are some examples of input files. So who hasn't? So these are very basic, so I can go really fast. I don't know if you have already submitted. Who hasn't submitted ORCA calculations and would like to? Or okay. No, so all the others have already do calculations, so no. Okay, so I'm going to go fast anyway, but I will leave this here. So I will send to Bipro then the slides and he can send it to you. But basically these are options. These are, okay, I'm requiring an unrestricted calculation. This is a pure functional, a double zeta basis set. This is auxiliary basis set for some approximation that makes the calculation faster. Another one, this is some grid options for numerical integration that's necessary for DFT, a request optimization and frequency. Then these are settings for how many processors. This is for outputting all the orbital information for plotting. If you don't do this, you cannot plot in Chemcraft or Avogadro. And these are, okay, I give the charge and the spin multiplicity hydrogen molecule as an example. This is another option with a pseudo solvent. I like a calculate include a continuous polarized. Sorry. Yeah, polar. I don't remember what the second C is. I forgot, but continuous polarized charge model. Circular. No, it's not circular. No. Conductor-like polarized continuum model. Yeah, that's it. So you do that whenever you want to actually calculate anything that's going to be in solution. Do that. It really affects the stuff. Then, okay, there are more stuff like that. Other examples, if I had more time maybe, but these are very basic. It's just examples that you can copy paste and start from that if you want to try something. This is for plotting spin densities, for example, like number of points in each dimension to get a better quality plot or not. Then this is an example of a spin density of a corolle, just to show what you can get from this type of calculation. Of course, this would be the coordinates of the corolle. Then you can calculate EPR with this. Then you should go at least for this and maybe like quadruple zeta on something like copper if you want accurate results for some of these parameters. So these are hyperfine contributions. Again, I want to go faster, so I won't go into what each of these is, but these are more or less what I would use to calculate EPR spectra of EPR parameters of something that has a copper complex. Okay, this is an example of an output so these are different examples of things you can calculate, but I will go faster. So this is what you would get, the G matrix of a certain, I don't remember which molecule. Okay, it was, probably not this one, but this is like, it gives you an output file that contains it gives you your geometry plus atoms which are noble gases like neon, argon, and xenon, I don't remember, that allow you to draw basically the G matrix is a matrix, so it has like vectors that point into directions, and in each direction you get a value of the G matrix. So basically this allows you to like put this into Chemcraft or something, and then you know where to draw the arrows for the G tensor. So you can code like this. I use this. This one is reversed. I put this on the other side because of a convention of how the X, Y, Z are ordered. So basically I can use the output to draw myself these arrows I drew myself. So this is Jesse's low spin cobalt complex. So this is a similar thing for hyperfine matrices. So you can see like for a certain hydrogen, it will give you the matrix, but usually you're going to only measure EPR like in fluid solution, like at least to get these splittings usually. So then you care only about the average, that's the isotropic part. So don't expect these values to be really good. They will be close like to the experiment, but maybe the experiment is like 6 megahertz, and this will give you 4 megahertz or 8 megahertz, and that's good enough. Don't try to get exactly. But if it tells you that for a certain hydrogen, the hyperfine splitting is 60 megahertz, and experimentally you see 6, then that's suspicious. That probably means that the structure is not exactly the one that you think you have in solution. But don't expect perfect agreement in EPR. So, okay, this is blank. So broken symmetry calculations, these are also very common. So you have, when you have a singlet, it's something that has a total spin. Actually, the spin square is 0, but the components of the spin is also 0. And you have the triplet, for example, that the total spin is 1. That gives you a squared spin mean value of 2, I think. So that would be 1 times 1 plus 1, like S times S plus 1. And then you have 3 different projections, ms plus 1, 0, minus 1. And you want to calculate these gaps. This is very common, like the radicals or like integer spin metal systems and stuff like that. So there are, you can calculate, so this is maybe somewhat loose, maybe there's a factor of 2 or something, but this is more or less the singlet triplet energy gap, allows you to calculate the exchange coupling between electrons, called J. It's not the same J as the Coulomb integral, okay? So that's a Heisenberg-Dirac-Van Vleck Hamiltonian. So in broken symmetry approaches in DFT, the problem is that you can write the triplet, the ms equal 1 and the ms equal minus 1 components of the triplet with a single Slater determinant, which would be this one. But you cannot calculate the ms equals 0 components of the triplet or the singlet with only one determinant. So in principle, you cannot get that from DFT. You could use CAS-SCF or another method. So what you get are called the one determinant wave functions are called broken symmetry because it does not contain another counterpart that has permuted, I think, the electrons or the spins, I think. For that, you need a second Slater determinant. So these broken symmetry solutions, wave functions, can, allow you to express, you can express the true singlet and the true triplet ms equals 0 as a combination of these broken symmetry solutions that you can get from DFT. So you can derive from that a formula for the exchange coupling and a formula for the true singlet triplet energy gap from these broken symmetry solutions. And okay, it doesn't matter that those animations are random, but basically it's an approximation that allows you to estimate through a single determinant method an exchange coupling that you could only in principle calculate it using a multi-determinant wave function method. So you request this using broken symmetry. So if you have only 2 electrons, you can put broken sim 1, 1, and you start from the triplet state, and the Orca will do the work. You usually don't need to worry. And it will print the energies and stuff, and it will print different J's. You have to always keep in mind how the Heisenberg-Dirac van Vleck Hamilton is written. There's a 2 in here, so J in here is written like this, and the singlet triplet gap is probably twice as much. So the high spin minus broken seam energy is not the singlet triplet gap. It's, under certain approximation, is half of it. It's not exactly half, that's why you get these numbers. These are different formulas, but if you calculate this, you get this number, and you put it here, you can see that the 2J is actually the singlet triplet gap. Okay? So more or less twice this number. Not exactly twice, but more or less. So don't get confused with that. Like, the broken symmetry is not the same as the singlet, it's in between the triplet and the singlet. So transition states, maybe someone is interested in this. So this is also a work that I did only the theory, all the others did the experiments. Some of them didn't do anything, any of the two, just they are there. But so this is the Hoveda group's catalyst, is a ruthenium catalyst that does this, how is it called? Like when you metathesis between olefins, yes. So for polymerization, I would say, or well, actually many things. But so these are calculations of possible inactivation routes for this catalyst. One of them is the consecutive attack of 2 water molecules. So basically the first one, now, okay. So the first water molecule approaches, this is a reactant, then it goes to a certain distance, transition state, and then it binds to the ruthenium, and one chloride, I think it kind of dissociates. This is an intermediate product, and then there's a second water. So those are possible routes of decomposition. It's not that we know that this is happening, it's something that could be happening. Another one is oxygen. So this is an oxygen molecule, although it's partly diffused there. It approaches there, it forms like a transition state binding to the ruthenium and the carbon of one of the ligands. It goes, makes an intermediate, and then it breaks and it separates like a ruthenium oxo moiety and a benzaldehyde. So how do we calculate this, or at least how do I do it? Which I'm not really an expert in transition states. I've only maybe calculated for 2 or 3 projects. What I do is a scan first. I start with, for example, I draw the molecules and stuff like that, and I know that ruthenium is atom number 49, the carbon that I want is 52, so I'm going to do a scan for breaking that bond on the last step here. So I start from 2.01 angstrom, that was more or less the equilibrium distance, and I could also like put a minimum, maximum distance and number of steps, but I wanted to have closer distances at the beginning and then more distant ones. So I put like, I think 18 points or something, 2.01, 2.05, and then I elongate the distance. So I call the scan. What I'm doing here is, after trying many things, I'm using B973C, which is a cheap functional or a cheap method, but it's kind of accurate. Loose self-consistent fields so that it will converge faster, and I use tolerances for the geometry optimization that are, I think, twice as large as the normal ones. Why? Because after getting tired of spending weeks and weeks calculations we didn't end or that crashed, I loosened all the stuff because this geometry scan is just like a preliminary picture of what's going on. Those are not the end results. So I do this, and I get an output file, and I get a lot of files with these are the coordinates of all the intermediate optimized geometries for each scan distance. And I get a graph like this. If I plot this in origin, I get like the ruthenium carbon distance, it starts at 2.01 angstrom, it increases, and then there's a jump because there's a reorganization. So these plots are like it's a slice of a multi-dimensional energy surface. So you can have these jumps because while this distance did not change much from this point to this one, the rest of the molecule rearranged. So that happens, like you are seeing the scan and suddenly something stays quiet for a while, and then all the molecules starts moving around and it finds a new conformation. So you can have these jumps. And this is the final. So these are the structures for, so this is a guess, a possible guess for transition state. So I take this geometry, and this geometry, which are these ones, as guesses for a subsequent calculation. So I did what it's called a NEB calculation. So sum NEB is because NEB is called Notch Elastic Band method. It's a method that finds a minimum energy path from reactants to products through a possible saddle point, which is a transition state. Saddle point is a minimum of energy in all coordinates except for one, which is the, I don't know how it's called, the relevant coordinate of that transition state, which can be like a bond distance. No, could also be an angle and other stuff. So, and there are other stuff. So TS is that I'm going to do an optimization of the transition state afterward the NEP, but this has never worked for me. So you can remove these frequencies calculations. Also, I don't need to do it in this calculation. I can do it later. And then, okay, I write a lot of stuff for myself so that I know where the files come from. It's very important. I use these big names that tell me exactly, like scan for oxygen, for ruthenium carbon breakage, and GF and whatever. I have these 2 or 3 letter codes that allow me to, like, each file has a different code. So I can find them later. I'm sure that GF is different from GH or GI or whatever. So I start from the coordinate GF001, so that would have been this one. And I put NEB for N file, the last one, the number 18, that would be on the left. And this is optional, but the possible guess of transition state, I put this one. It's optional because sometimes I can find it just from the beginning and end. Then this part would be for the transition state optimization, but it's not necessary here. So what I get is something like this. This is the animation that was produced by the NEB. So it starts, a certain distance, and it breaks the bonds and stuff like that, and gives me like a possible pathway for this reaction. And this is obtained through this file. It's a trajectory file. MEP means minimum energy path. So this is what the NEB calculation found to be optimal under these whatever conditions that I put, the functional and stuff like that. So this is an XYZ coordinate file that I can animate with Chemcraft. And this is more or less like if you plot there's a NEB all or something like that file that contains not only the optimal, what I showed the animation for is these last steps, but actually there's another file that gives you all the different attempts that was doing at this minimum energy path while optimizing. So you can see that it starts from, this is your first structure, last structure, and initial transition state, it has this energy. And this cycles a lot, and it goes optimizing this stuff. So this can reduce, nothing here is not changing this energy or this one, but you can put an option that also optimizes the end points. But you can see like the path in between and the energies of the transition state are getting optimized. So you are, imagine a surface like mountains, like here in Stuttgart, and you are kind of like moving around to find the easiest walk from one side to the other of a mountain. That's what basically it's doing. So it will give you an optimal path, and that would be a possible transition state. It doesn't, I don't know if it's a real one, but it's an approximation to the real transition state. So this is what we have calculated, this part of the graph with this different stuff. And what I wrote it here. What I do with that after the NEB is whenever I have tried an optimization of transition state, which is another method that Orca uses for finding transition states, I usually fail. I have not failed for simple organic reactions, but with this transition metal stuff, it doesn't, like, you want to optimize the transition state, it actually goes to one, either the reactants or the products. So that's a shortcoming of Orca, that basically they wanted to, like, people complain about that in Orca, and that's why they use Gaussian or stuff like that. but I think that what they did in Orca is switch to this NEB method, not like try to get a better algorithms of the opt-TS, but just switch to the NEB, which is much better. So what I do that then is, after I did the NEB, I took the endpoints and I re-optimized them, and I checked that they more or less look the same, and I calculate frequencies, but the transition state that I got from NEB, I don't try to re-optimize it. I just calculate frequencies and verify that there should be one imaginary frequency. So this is more or less like a summary. Relaxed surface scan to identify reactant product and positive transition state. You can do a notch elastic band, and then I do opt plus frequency on the reactant and product, but only frequency on the transition state. And it will give me like, okay, this is something that could be happening. I'm not saying that this is like true, but you know, it's a possible reaction, you know, a possible barrier and possible transition state. It was not the point of this paper to try to be quantitative about these reactions, because we were speculating on what could happen. You can also use opt-TS, and this will work in maybe simpler reactions, but doesn't all the time work, and it can be really difficult to try to get it to work, so I go this route. And this is QM. Okay, so maybe I should stop it here. So, but this is just how to do multi-level calculations, and I can maybe go like very fast. So this is QM XTB. XTB is some semi-empirical method that I will use only for the solvent, and I do other stuff. In here is a scan, but it could be anything, and I define the QM atoms to be these atoms only, that are these acetic anhydride and isopropyl amide. This was just an example for a YouTube video, and then I can calculate, this is a scan, and calculate possible transition state and stuff like that for a reaction that's a nucleophilic attack on a acetic anhydride, but it's done using these DMF molecules are all treated on a lower level, so it allows me to consider the solvent explicitly, but not with a not so expensive calculation. And these are some other keywords about QM or QMMM. So I haven't done QMMM because I haven't figured out how to define a force field in Orca. I don't even know what force field to use, because most of them are for proteins and stuff like that, and I don't work with proteins. I don't know like a simple force field for solvents. There probably is, but I haven't found it. And that's it. Sorry that it took longer. So maybe if you don't know, like I have a YouTube channel where I used to post stuff. So these videos are mainly related to transition states and scans, some like QM. Some of what I show is from there, and these are on broken symmetry calculations, and there are some other stuff on plotting and other stuff. If you want to subscribe or maybe comment in the videos, it helps. Maybe someday I will get money. Yeah, and that's it.